Hello and welcome to ACSA Academy. This is our fifth video from the quadratic equation in our 1MSET series. And in this video, we'll be moving towards completion of the chapter in which we'll be covering some of the remaining topics and we'll be solving a lot of examples which will help us to be able to deal with any kind of problem that comes from this particular chapter. So let's get started. Coming to this difference of roots, let us recall what all we have learnt about quadratic equations till now. Just in brief, we know that the general form of the equation is ax squared plus bx plus c equal to 0, where these a, b and c are the coefficients and x is the variable, and we take its roots in general form to be alpha and beta, such that we have already seen that the expression for alpha and beta can be derived as alpha and beta separately for both. We usually do that. For them, we derive the value as minus b plus minus root over of b squared minus 4ac upon 2a, and this particular equation is called as d, so you can also write it as minus b plus minus of root d by 2a, where this d equal to this particular expression. We have already seen the derivation of all these things, and along with that we have also seen the sum and product of the roots. We know that the sum of alpha and beta is minus b by a and the product is c by a in terms of these coefficients a, b and c. Again, we have seen the derivation and the implications of this. We have also solved a number of problems based upon them. For example, if the roots of this particular equation are alpha and beta, then find an equation whose roots will be alpha by beta or alpha square plus beta squared upon beta minus alpha, something like that. So we have already solved those kind of problems. But now coming to difference of roots. What does this imply? And why do we have this modulo sign over here? Let us see. Now we know that alpha plus beta and beta plus alpha both will be same because it is a commutative operation. We have all those reflexive, associative, commutative, and from that this addition comes under commutative. But when it comes to subtraction, definitely alpha minus beta may not always be equal to beta minus alpha. Now why did we say always? Because there are different cases, like it depends on what is the value of your d. For example, let us analyze it over here. We already know that d, which is this particular equation, b squared minus 4ac. So now there are multiple cases. You can have d greater than 0, d equal to 0, and d less than 0. So when your d is positive, then the root of d, which means the root of this particular equation, under root of b squared minus 4ac, that would give some positive result. And hence in that case we get distinct roots. Alpha and beta are not same. Then coming to case 2, when d is equal to 0, in that case we have alpha equal to beta. There is a single root of that quadratic. What is an example of such a quadratic equation? You can say x squared minus 4 equal to 0. Now for this quadratic, if you try to find the root by this completing the square method, what will you get? Minus b, which is b is 0 over here. So minus 0 plus minus root over of b squared. What is a b squared? Again here b is 0, so 0 minus 4a. What is a? It is 1. And what is c? Minus 4. So this is what it becomes upon 2a, which means 2 times 1. So that gives us plus and minus of root 16, which is 4. So plus minus 4 by 2, which is plus and minus 2. And that is what we know would be the value of this. X squared equal to 4 will have two roots, plus 2 and minus 2. But was this the case when d was 0? This was the case when the coefficient b was equal to 0. And in this case, we have got the d to be positive, which means it has two distinct roots, that is plus 2 and minus 2. So it falls under this first category. let us try to see an example for this second category when d will be 0. For this, you can take an example such as the whole squares. For example, if you have x minus 1 the whole square, such kind of quadratics, you can expand it and write it as x squared minus 2x plus 1 equal to 0. For this, if you try to write down the completing square method, what will it give? It will give minus b, which means 2, plus minus of root over of b squared, which means 4 minus 4ac upon 2a. So it is giving 2 by 2, which is 1. So there is only one single root. Both alpha and beta take the same value over here. So that was our case 2. And then coming to case 3, those which will be having imaginary roots. For example, like coming to the same x squared minus 4 example, here if it were plus 4 instead of minus 4, then what would it have resulted into? Then it would have been minus over here, and that would have resulted into root of minus 16 by 2, which we know is a complex number or imaginary roots, you can say. So in that case, your alpha and beta both are complex. So now, depending upon these three cases, we can differently define what the difference of roots would actually mean. If it was your case 1, then alpha minus beta and beta minus alpha both would be different. But in such cases, what do? Is we take the absolute difference, which means you will calculate any one of them and then you will take the modulo sign, so that it does not matter which one is greater, which is smaller, or what fashion have you taken the difference, because ultimately we're taking the absolute value only. And then coming to this case 2, here the difference is always going to be 0 because both are equal. And for this case 3, in which we have complex roots, usually don't define the difference of roots for this case. So we will only be considering cases 1 and 2. And now let us go on to derive the actual expression for this difference of roots in terms of coefficients a, b and c, just as we did for the sum and product of roots. In that way itself, we will also find an expression for the difference. So now let's do that. Okay, alongside you may also try to do the derivation because it's quite simple. We don't need to use much of the mathematics over here. Alright, so let us start with what we already have. Sum of roots as minus b by a, product is c by a. And what do we want to find out? The difference. So for this, what we can do is we need to find the relation between alpha plus beta, alpha minus beta and alpha beta. So can you think of any such expression where all three of them can come together? You can think of an equation such as the whole square one, which we had just seen. We can say that if we take alpha plus beta the whole square and if we take alpha minus beta the whole square, then can we bring this into the form of alpha beta? Yes, it is possible. If we simply subtract them, then let us see what happens. Now for the subtraction, what we'll do is we'll simply expand them using the formula which you already know, and then we will substitute their values that again we have written above. So that gives us alpha squared plus 2 alpha beta plus beta squared minus of alpha squared minus 2 alpha beta plus beta squared. And when we open the bracket, it will give minus alpha squared plus 2 alpha beta and minus beta squared. So now can we take anything common or can we cancel out anything? Yes, we can cancel out alpha square and beta square, and finally we'll be left with only one single term, that is alpha beta. So the result that we get is these two are cancelled, we get 4 alpha beta. So now to substitute their values, we know that this alpha plus beta is minus b by a whole squared minus of, we don't know this yet. This is what we need to find out as the difference, equal to 4 times the product, which is c by a. So now solving this expression, what do we get? Alpha minus beta the whole squared equal to b squared by a squared minus 4c by a, and we can also write it as b squared minus 4ac upon a squared. So this is the expression for difference squared. This is the square of difference. We want only the difference. So now we will take the square root on both sides. So that will give us, taking root of this with a modulo sign, that would be alpha minus beta, the absolute value equivalent to root of b squared minus 4ac upon a squared. Now we already know that this expression b squared minus 4ac, it corresponds to the determinant d. So we can replace that with d. So it will give us root of d upon a. Yes, we can also take the absolute value again over here, but as per the standard definition of quadratic, we always take the leading term to be positive. If it is negative, then we multiply the entire equation with a minus sign and we convert it to positive. Hence, there is no absolute need of taking a modulo over here, but we can also take no issues with it. So from this, we derive the difference of roots to be root of d by a. So this is the expression for difference of roots, and it will hold in all the cases. Case 1 and 2, which we have seen. In case 2, it will definitely lead to 0. And in case 1, whichever way you do, the result is always going to be root d by 8 itself. So now let us take an example problem on this and see how this can be applied in problems. In this problem, we have been given an equation for which we need to find out the difference of roots. Now, as we can see, this particular equation is not in the standard form of a quadratic equation. So, how do we approach this? Can we see some common terms in it which we can combine and we can somehow convert it to a quadratic equation? Let us try to have a look at it. The leading term we see is 4 raised to x, and this middle term is 2 raised to x plus 3. So do we see something common in this? They are the powers of 2. So can we write this 4 raised to x as 2 raised to 2x? Are both the things same? For this, let us go into the bases and indices which we have learned, that a raised to m and then that raised to n, it is equivalent to a raised to mn, and then a raised to m into a raised to n equal to a raised to m plus n. All those indices formulae which we had learned, let's just recall them and try to apply them over here. So yes, we can convert this 4 raised to x as 2 raised to 2x because 4 is 2 squared. So we actually, what we did is we wrote 4 as 2 squared and then this x was there, so that became 2 raised to 2x. Then here we already have this 2 raised to x plus 3. We can separate out this 3 from here and we can write that as 2 raised to x into 2 cube. We just applied this one in the reverse way. So now we can convert the given equation into 2 raised to 2x minus 3 times of 2 raised to x into 2 cube. What is it? 2 cube is 8 plus 128 equal to 0. You can again simplify it as 2 raised to 2x minus this 8 and 3 combinedly form 24. 24 times 2 raised to x plus 128 equal to 0. So now we see something of the familiar form. Here we are having a square term, here we are having a linear term. So yes, now we can get to convert it into a quadratic equation. How? We can simply replace 2 raised to x with, let us say, t. Then what will be the advantage of doing that? Let us see if we are able to convert it into a quadratic. After replacing, we will be able to write that as t squared, because this is 2 raised to x and that squared. This is what the first term is. So we can replace it with t squared, then minus of 24t plus 128 equal to 0, wherever t equal to 2 raised to x. So now we have got an actual quadratic equation in the form that we already know. So now can we solve it? Let us see if we can do it by factorization method or if we need to apply the completing square. The product which we have been given is 128. So are there any factors possible? For 128, let us find out. It will be 2 times 64, 2 times 32, 32 and 4. No, that will not give 24. So again 2 times 16, 16 and 8. Yes, this can be possible. So we have got the factors to be 16 and 8. So this will be factorized as t minus 8, t minus 16 equal to 0, which means the value of t which will satisfy this equation would be 8 and 16. Those are the two roots that we have got. So now what is the difference of the roots? Is it 8? There are these two roots, 8 and 16. So we can simply take the difference. 8 minus 16 equal to 8. Is that our answer? No, it is not. Why so? Because t is not the root of our original equation. We manipulated the original equation and converted into this familiar form. But we have been asked the difference of roots for the original equation. So now we will be needing to convert it back into that form. And how we will do that? Using this particular expression, that is t equivalent to 2 raised to x. So using this, we will again convert back that t into x. What we'll do? We will say 2 raised to x is actually what is having the values as 8 and 16. So now there are two cases. 2 raised to x equal to 8, 2 raised to x equal to 16. From this we get x equal to 3, and from this we will be getting x equal to 4. So the final two values of x that we have got are 3 and 4, and those are the roots of our original equation that has been given. So for this particular equation we need to find out the difference of roots, and we have already got the two roots to be 3 and 4, so their difference will be reported as 1, and that will be our answer. So now you might be wondering, why did we find out the roots here and then take their difference instead of applying the formula which we have just seen, root d by a? Why didn't we use this formula? Now the thing is, we have also discussed this at the time of sum and product of the roots, that sometimes it gets difficult to actually find out the two roots and then take their sum or their product. Instead of that, we can manage with the coefficients itself. But now in questions like this, as you have already seen, it was more easier to find out the roots itself and then take their difference. The reason being that our original equation was not in the standard quadratic equation form. So there you cannot say that this is our A. A is 1, B is 3 and C is 128, and then you start applying that formula. No, it will give you wrong answer, because for that to be applied, equation needs to be in the standard form. That is what we did. We converted it into this standard quadratic form. So now here, why didn't we apply the formula? Because this is not the quadratic for which we wanted the difference of roots. We wanted the difference for the original quadratic. Hope you are getting it, because this is the modified equation. The difference of roots for both of them will be different. We have already seen. For this one, the roots were 8 and 16, which means the difference is 8. But for the original one, the roots are simply 3 and 4, with the difference being 1. And that is what we wanted. So this is the reason why for such questions we approach it like finding the actual roots and then taking their difference. Okay, now let us have a look at another problem so that things become even more clear. Now moving ahead, the next topic we are going to dig deeper into is equation versus identity. Because we have already touched it in one of our previous videos, we already know what an identity is, what an equation is. Let us analyze it a little further and solve some examples on this. So now, talking in general about the polynomials, what is it? A polynomial is of the form an x raised to n plus a n minus 1 x raised to n minus 1 and so on till a0, and this becomes a polynomial equation when you write it as this expression equal to 0, and every polynomial of degree n has n roots, which means the number of roots of a polynomial equation is same as its degree. As in case of quadratics, we know that it always has two roots. Now yes, there can be different situations that if your d is positive, then you will have distinct roots. If your d is 0, then you will have identical roots. But even in this situation also, there are two roots, just that their value is same. And if your d is negative, then you will have imaginary roots. But then again, those alpha and beta, there are two distinct roots and both of them exist in the conjugate form. So whatever case you consider, a quadratic always have two roots. Similarly, a polynomial equation always have n roots if its degree is n. But then what about an identity? This was the normal equation which we are aware about. But talking about identity, let us consider this example. I say that this ax squared plus bx plus c equal to 0. This equation has three distinct roots. Will you agree on this? What are the different parameters that you would be considering before you agree or disagree this particular statement? Now looking at it, we see that it has the highest degree as 2, so we call it a quadratic equation. But is that true? Let us jump back to the roots. What was the actual definition of a quadratic equation? We learned that its highest degree is 2, fine. It has three coefficients a, b and c, fine. But there was some condition imposed upon them that a cannot be 0. This was one of the most important conditions, failing which this equation will cease to be existing as a quadratic, because now I can add 0x cube in front of it, 0x raised to 4 in front of it, and so on. So will it keep increasing its degree? No, it won't. The leading term can never be 0. That is one of the conditions we need to ensure before calling anything to be a quadratic equation. So now coming back to this, is it a quadratic first of all? We are not sure because they have not mentioned anything about A, B and C. Whether they are positive, negative, whether A is 0 or not, like nothing is known about them. No relation is known between them. They are simply saying that this is an equation and it has three distinct roots. So in which scenario is it possible? How do we call it an identity, or how do we say that it is not an equation? So the only possibility in this case would be all of its coefficients would have to be, all the coefficients must be rather 0. 0x squared plus 0x plus 0 equal to 0. This is what it has to be. Means A, B and C, all of them need to be 0. Then only you would be able to say yes, this has 3 distinct roots, 4 distinct roots, 1000 distinct roots. Why so? Because in this particular equation, whatever value of x will you substitute, the LHS and RHS will always be same. As you can see, the value of x, whatever you put, anyway it is getting multiplied with a 0. Here also you have a 0, here also it is a 0. So whatever x you put, it will always be satisfied. So you can say that it has not 2, 3000, rather infinite roots. So this is an identity. So now we are clear what does an identity mean. It will always satisfy, like any value of x you put, it will be satisfied. So an identity is something which has infinite roots. When can you say that a given equation is not actually an equation, it is rather an identity? When will we be able to say that? When you see that its degree seems to be 2, because we are looking at it, we don't know right now what is its value, is it 0 or not, we are not aware of it. So just by looking at its degree, if it seems to be, let us say something k, and it has been told that it has the number of roots which is greater than k, then you have to be sure that there is something wrong. This is not a standard polynomial. It would rather, there is a possibility that it can be an identity instead. So then this asks for further investigation. We need to check if the leading term is 0, or what coefficients are, if all of them are 0, or what is the reason why it is having more number of roots than its degree. So that is what takes us to the concept of identity. So now let us take an example and try to understand with it that how will we be able to approach the problems from this topic. This example, we have been given this equation f of y equal to f1 of x y squared plus f2 of x y plus f3 of x. So seemingly it looks like f of y equal to 0 would be a quadratic in y, with its coefficients being these a, b and c as functions of x. So if we write it in the expanded form, because these functions have been defined over here, we will get f of y equal to, instead of f1 of x, we will write x minus 2x minus 3 times of y squared plus f2 of x, which means x minus 1 x minus 2 times y plus x2 minus x. So this is like representing a quadratic equation in y. If you say f of y equal to 0, then these a, b and c will be its coefficients, and this ay squared plus by plus c equal to 0 will be a quadratic in y. It seems so as of now for the moment, but we need to prove that it is an identity rather. And for what values of x does it become an identity? That is what we need to determine. So now we just saw what an identity is in terms of y. If our variable is y, then this needs to be become of the form 0y squared plus 0y plus 0 equal to 0. Then only it will become an identity in y. And what do we mean by an identity? Like over here, if this has to be an identity in y, means whatever value we put for y, it should always get satisfied. So this f of y equal to 0 has to become something which will satisfy all values of y. And when will that be possible? When all of its coefficients a, b and c, all of them individually become 0. Then only it will be able to become an identity in y. So basically what we need to do is, we need to make all a, b and c as 0. And for what values of x will that be possible? That's what we will determine. So let us start with a. For what values of x will it become 0? 2 and 3. From these two factors, we can determine that. Similarly for b, it will become 0 for 1 and 2. For c, it will become 0 for x equal to 0 and 2. So now collectively we have got 0, 1, 2 and 3, 4 values of x. So for all of these values, will f of y equal to 0 become an identity? Let us check out. If we take x equal to 0, then only this c will become 0, a and b will still be there. Because if we substitute 0, then this will become 0 minus 2 and 0 minus 3. So minus 2 minus 3, 6. This will become minus 1 and minus 2, which is 2. So like a and b are not getting cancelled out, they are still there. So 0 is not the correct answer. Similarly, if we take 1, then only this b will be cancelled out, a and c will still be there. So again, that is not true. Then coming to b, which is 2, 2 is a common root for all of them. A, B and C, all of them have 2 as the common root. So when we substitute x equal to 2, then A, B and C all will independently become 0. And then we will get this particular equation, that is 0y squared plus 0y plus 0 equal to 0, which we call an identity. Similarly, for 3, only A will be cancelled out, other 2 will be there. So as a result, we got only one particular value of x, which is 2, for which this f of y equal to 0 will become an identity. So this is our answer, that only for one single value of x, that is 2, we will be getting f of y equal to 0 to be an identity in y. So this is how we could solve this problem. Now let's move ahead. Next problem that we'll be dealing with, we need to find out the number of imaginary roots for the given equation. What is the equation? F of a multiplied with g of a equal to 3, where both of these functions have been defined over here. So ultimately, what is it that we get? Instead of f of a, we will write a minus 1, a minus 3, and in place of g of a, we can write a minus 2, a minus 4 from here equal to 3. So this is our equation for which we need to find the number of imaginary roots. Now directly looking at it, it seems to be a biquadratic equation because there are 4 factors. When we will multiply all 4 of them together and then when we will write it in the standard form, it will become a biquadratic equation. But we cannot directly solve them. Biquadratic equation cannot be directly solved using the formula method or the factorization method that we know. Here the catch is that the right hand side is 3 instead of 0. If it was 0, then we could directly say that the roots are 1, 3, 2 and 4. But that is not the case. It is 3 instead of 0. So how can we actually solve this and get its roots and identify if they are real or imaginary? So now one approach that can come to our mind is, what if we try to combine them 2 at a time? Like if we combine these 2 together and then these 2 together, let us try to multiply a squared minus 4a plus 3. That is what this will become. And the second half will give us a squared minus 6a plus 8 equal to 3. Now, does it look something good? We don't know how to move ahead. These are two polynomials, quadratic polynomials you can say, and their factor is giving 3. So doesn't seem something very much familiar to us, or something which we can take ahead. So should we go for any other combination like these two and these two, or these two with these two? What should we choose? Let us say the trick over here can be, if you see, the sum of this 3 and 2 gives 5. Similarly, the sum of 1 and 4 also gives 5. So let us try to multiply, take these two together and these two together, and let us see if it converts into some better format. So let us shuffle the terms, take them alternately, and then see what do we get out of it. So we will take a minus 1 and a minus 4 together, and a minus 2, a minus 3 together equal to 3. Now let us again expand them in the usual way. This will become a squared minus 5a plus 4, a squared minus 5a plus 6 equal to 3. Now do we see something good? We can see that this is common in both of them. So now if we go with the substitution method, and if we substitute a squared minus 5a equal to something, let us call x, then what will we get? X plus 4, x plus 6 equal to 3. Now this looks good. We can simply expand it and convert it into a quadratic equation. It will become x squared plus 10x plus 24 equal to 3, or x squared plus 10x plus 21 equal to 0. Now we have got a standard polynomial and we can solve it. Are there any possible factors for this? Yes, 7 and 3. So this will become x plus 7, x plus 3 equal to 0. So for this, the roots that we get are minus 3 and minus 7. So now what next? We know that this x is what we have got these two roots minus 3 and minus 7 for. But our original equation was in terms of a, and that was the substitution that we used over here. So now we need to convert back this x into a and find out what is the value of a that we are getting, because that is originally our variable, right? So now let us substitute these two values of x over here and see what is the value of a that we get. So a squared minus 5a equal to x was there, and for x we got two values, minus 3 and minus 7. So let us independently substitute both of them and see what a do we get. A squared minus 5a equal to minus 3, a squared minus 5a equal to minus 7. So these are the two quadratics we get again. So now as you can see, both of them are quadratic equations. So we will get two roots, let us say alpha 1 beta 1 from here and alpha 2 beta 2 from here. So in total we will be getting 4 roots, and that is what is expected as well, because our original equation was a biquadratic. So we must definitely get 4 roots. So now let us solve and get all the 4 roots, and then we will determine what is the number of real roots and imaginary roots. So coming to the first one, now there is no factorization that can be applied over here. So we'll go with formula method. It will become 5 plus minus root over of b squared, which means 25 minus 4, 1, 3 upon 2. So that is 5 plus minus of 25 minus 12, 13 by 2. So now these are the two roots that we got. Is it real or imaginary? It is real, because yes, you can definitely say that it is irrational because there is this particular term, but this plus 13 inside a root, it is not a negative term, so definitely it is real and irrational if you want to be more specific. Now coming to this side, the roots will be 5 plus minus of 25 minus 4, 1, 7 by 2. So that is 5 plus minus of 25 minus 28, that is minus 3 by 2. So these are the next set of roots that we got, but here this root of minus 3 becomes imaginary term, which means these roots are non-real or imaginary. So we have got all the 4 roots, and among them we can clearly see that 2 roots are real and 2 are imaginary. Why only 2 and 2? Okay, what were the possible options for this? Real and imaginary. Either we could have 4 0, 2 2, or 0 4. 1 3 3 1 was not possible anyway because these roots always occur in pairs, in conjugate pairs in case of non-real or imaginary numbers, and in simply these pairs as we saw over here in case of real. So these are the only three possibilities that could have been possible. If you see 1 3 3 1 in the option, just discard that simply because you can never have one real root and three imaginary roots for a biquadratic or for any polynomial for that sake. They will always be in even number pairs. So for this problem, we have got two real roots and two imaginary roots. So our answer for this will be 2 in this case. This is another popular kind of problem which you will definitely be dealing with when doing this particular chapter. Let us see what has been given. They are defining a function f of x which is x squared minus 6x minus 2. And then they are saying f of a equal to f of b both are 0 such that a is greater than b. So simply this statement is trying to say that x squared minus 6x minus 2 equal to 0 is a quadratic whose roots are a and b such that a is greater than b. That is what they are trying to say just by changing the language, trying to confuse you. Don't get confused. Now further, they are defining another function g of n equal to a raised to n minus b raised to n. Now these a and b are the roots of the given quadratic. Upon those roots, another function has been created. And finally, they are asking the value of this expression g of 10 minus 2g of 8 upon 2g of 9. So yes, seemingly it looks difficult, but it is not that difficult. Let us see how. And one thing is for sure over here that this given quadratic does not have easy factors. So there is no possibility of finding the actual roots and then using them in place of a and b. That's not possible over here. You will be needing to deal with irrational numbers. If you're ready to do so, then please go ahead. Otherwise, the easier approach for this problem would be to deal with the sum and product of the roots. So here, the sum of roots a plus b will be 6 and product of roots ab will be 2. So now using this information, can we directly use this function and should we go for finding all the values of g up to 10? No, that will be a lot of overhead to be going with. Still anyway, let us try to find out what is g of 1. It will be a minus b, simply the difference of roots. And we already know here the modulo sign is anyway not needed because we know that a is greater than b. So that solves our problem. So simply let us write that as root d by a, which we know is b squared minus 4ac upon a. That will be the value of g of 1. So let us substitute 36 minus 4 plus 2 and 1. So that becomes 36 and 8, which is 44. So we have got the value of g of 1 to be 44. Should we go for finding g of 2? It will be a squared minus b squared equal to a plus b, a minus b, a plus b we know 6, a minus b we got 44. So the product whatever we get, that is g of 2. Now g of 3, 4, 5 up to 10. Should we go by that way? It will become very lengthy. So let us see if something better can be done. So for that, let us go to the expression that we want and let's try to simplify it if it is possible. It's given g of 10, which means a raised to 10 minus b raised to 10 minus of 2 times g of 8, which means a raised to 8 minus b raised to 8 upon 2 times g of 9, that is a raised to 9 minus b raised to 9. That's what we want. Let us expand and make the terms together. A raised to 10 minus 2 a raised to 8 minus b raised to 10. Now here we have a minus sign, and here there are these two minus that will become plus, but we have taken minus as common, so again 2b of 8. This is what we are getting. Let us verify. A raised to 10 minus 2 a raised to 8, fine. This is minus, that becomes plus. So yes, this is what we get. Denominator is 2 times a raised to 9 minus b raised to 9. Now what can be done next? We have decided that we will not take this add up to 10 times and not find the actual values. Then even we don't see anything common over here. Then what should be done? Let us try taking out this a raised to it and b raised to it common from the numerator. That will give a raised to 8 a square minus 2 minus b raised to 8 b square minus 2 upon 2 a raised to 9 minus b raised to 9. Done. What next? Now looking at this a square minus 2 and b square minus 2 and looking at the original equation, we see something good. What is it? This x squared minus 2, which means now we are simply going to replace this x squared minus 2 with 6x. If we take the 6x on the other side, then we get this particular thing. So now we will use that and it will just solve our problems. Let us see how. Now you might be thinking, how do we know that how do we know this in exam? How will this click in our mind that this has to be done next? How will it strike us? So the answer for all your queries is practice. Yes, this was a new type of problem, and if you are encountering it for the first time in the exam, then you might not be able to do it. It's a fact. So if you practice a lot during your preparation time itself, if you have if you have encountered all type of questions, then you will not see anything new in the exam. You will be easily able to click that in your mind and you will be able to solve it quickly. So yes, coming back, this is a raised to 8 and we are writing this a squared minus 2 with 6a. Similarly, b raised to 8 and we are replacing b square minus 2 with 6b. Yes, we can definitely substitute a and b in this because they are anyway the root of this equation. So in place of x, we can substitute a and b. That's what we did. Denominator is 2 a raised to 9 minus b raised to 9. So now next, it becomes 6 a raised to 9 minus 6 b raised to 9 upon 2 a raised to 9 minus b raised to 9. Now our problem is almost solved. We are just one step behind. What's to be done next? We'll simply take 6 common from the numerator and it will give a raised to 9 minus b raised to 9. Denominator was already 2 times of a raised to 9 minus b raised to 9. So yes, we are done. Simply cancel it out and we get 6 by 2, which is 3. So can you imagine that gigantic difficult looking expression which was given, g of 10 minus 2g of 9, 8, whatever that enormous expression was given over there, it got resolved to 3. And we solved this problem without all that headache of actually reiterating it for 10 times. We did not even find out g of 1, g of 2, nothing was required. We just used the sum, the product. Even sum product was not actually required at any place. The only thing which we needed was that we had to substitute that x squared minus 2 with 6x. From this we derived x squared minus 2 equal to 6x. This is the only thing that we used, and rest was simple mathematics, pure algebra, nothing more. So this was the main highlight of this question, that you should be able to grab, or this idea should come into your mind, that given a quadratic, you can shift this on that side and use these two. Or in other cases, you can shift this on the other side and use these two terms. Similarly, for this leading term as well. So that was the idea behind this question, and it was difficult looking, but as you can see, it could be easily solved. So now on the same grounds, here we have these two problems as the assignment for you to solve. Again, they are based on the same concepts which we dealt with in this and the previous videos. Let us have a look at the questions also. Here P and Q are the roots of the given equation. Then prove that the value of this particular expression, it is using the coefficients a, b, c and the roots p, q. So you have to prove that the value of this given expression is this thing. So that is a proof kind of question. Then the second one is, you have been given an equation and you have to prove that it is an identity. The same kind of problem we have already seen in this video. So these two problems are there for you to solve. Please solve them and post the answers in the comment section. Both are prove that type of question. So just let us know if you were able to prove it or not. We will be definitely having a look at the solution in the next video. Till then, stay tuned with ACSC Academy and all the best for your preparations.